Okay, now we're on a really, really important and a concept in chemistry. It's not going to go away. This one is a pivotal part of all chemistry courses from here on out. So you must know them how to calculate the molar this year. You're going to do it in term 2, you're going to do it in term 3, term 4, all next year. And then any chemistry that you do at university will be using the mole. It's kind of like it's the gold standard for what we need to use in chemistry when we're calculating anything quantitatively. So the mole is simply a way of counting things. So 1 mole of a substance is equal to 6.02 times 10 to the 23 particles. Now I am going to link to this video and it's going to show up here. So if you want to watch this video, you can go and watch that video and then come back here to keep learning about the mole. But the mole is just a counting method, kind of like a dozen. So I'm going to show you what I mean. So the mole uses this number called Na here, and this is the guy that came up with it. His name is not Avogadro, his name is Avogadro. So this is Avogadro's number. Okay, and he decided that 1 mole was going to be equivalent to this many particles in a mole. Okay, if you have 1 molecule or 1 atom of something, it is equivalent to 6 times 10 to the minus 20, 6.02 times 10 to the 23 over mole. Yeah, but you can kind of ignore this bit here. Mostly what I want you to take away is that 1 mole is equal to 6.02 times 10 to the 23. Now, you can keep saying it to yourself over and over again. You just need to know that number. So let's have a look here. If you have 1 mole of water molecules, you're going to end up with 6.02 times 10 to the power of 23. Now, that's how many molecules you have, because you have 1 mole is equal to 6.02. Now, in 1 mole of water, though, you're going to have 2 times the number of hydrogen atoms. And that's because over here, we've got 2 hydrogens in every 1 water molecule. So we can use the mole calculations to times that out. So we got 2 times 6.02 times 10 to the 24, which if we evaluate that, we should end up with 1.204 times 10 to the power of 24 atoms. And then, but with oxygen, there's only 1 oxygen present. So it's got 1 oxygen, make sure I write that out, in 1 water molecule. So it's just going to have 1 mole. Yeah, so 1 times 10 to the power of 23. So what we can do is we can use the analogy of eggs. So what you can do if you look at how many dozen eggs you have, if you count up how many eggs you had, say you had 24 eggs, you would divide it by 12 and that would give you 2 dozen. If you said I have 2 dozen eggs, you would times by 12 to get back to 24. It's exactly the same with the number of particles and the number of moles. Okay, and this is the equation we're going to use. So N in this equation is equal to the mole. The capital N is equal to the number of particles. And this Na, that is good old Avogadro's number. And that one is 6.02 times 10 to the power of 23. So here's another way of just showing you. Here is our equation. Let's have a look at my first example. So I want to figure out how many nitrogen molecules there are in 1.8 mole of nitrogen molecules. Okay, so the key here is that it's asking how many molecules. It's not asking how many atoms, because that would be a different question. So we use our equation. Yeah, we know the mole is over here. 1.8. We want to find out this, and here is Avogadro's number. So what we can do is we can multiply that out, and you end up with 1.8 times 6.02 times 10 to the power of 23, and you end up with 1.1 times 10 to the 24 molecules. Yeah. Now, if I was to change this and say I've got 1.8 mole of N2, how many nitrogen atoms? That's going to be different because now we have 2 in every one. So the total number of mole of nitrogen atoms is going to be 2 times 1.8 equals to capital N over Na. So we're going to end up with 3.6 over N by 6.02 times 10 to the 23. You're going to multiply them out. Again, my brain doesn't do that maths on its own. This is why we use calculators. We end up with the number of nitrogen atoms in N2 is going to be 2.2 because it's 2.16 times 10 to the power of 24 atoms. Okay, that's how you can calculate those. Let's just have a look through one more example. Oh, there's 2 more examples. So calculate the amount in mole of water from 3.8 times 10 to the 24 of water molecules. So this time we want to know mole. We've been given the number of molecules here. This one here is Avogadro's number. We multiply that, we divide them together and we end up with 6.3 mole of water molecules are present. Here's one more example. Again, you can pause, try it out yourself, then see how we go. How many oxygen atoms would be found in 1 mole, 1.35 mole of CO2? So remember here, we've got 1.35 mole of this, but we're talking about atoms. So that means to begin with, we're going to have 1.35 times 2 equals 2.700 atoms. Before we start, so there we go. This one here has figured out the number of carbon dioxide molecules. So if you substituted this in, this one here, they've just done the 2 down the bottom here. So it doesn't matter if you do the 2 at the beginning or if you do the 2 at the end, you should end up both times with this answer here. Okay, there's one more example. If you have 1 mole of methanol, so here is methanol here, you can see that it's got 1 carbon, it's got 1 oxygen, and it's got 4 hydrogens. So that's its empirical formula. So if you have 1 mole of methanol, you've got 1 mole of methanol molecules. We're happy with that. We've got 1 mole of oxygen molecules because there's only 1 of those. We have, oxygen atoms. We've got 4 hydrogens, so we're going to have 4 mole of those. Then if you multiply them out, so this is going to be times 6.02 times 10 to the 23. It's going to give you your atoms, so on here, and then you can add them all together and figure out how many atoms in total that you have.